So, before I start, does anybody have any questions about the project progress, the results? Because I get a lot of emails about some concerns about the results. Did any of you have any questions so far?
About the shear leg, how can I calculate the ratio of shear leg? Because
So, like, let's say, for example, you have, this is the first column here, and this is the first column here. And let's say that this is the tension at this column, and you draw this something like that. Okay?
yeah.
So that's how it is. So the thing is, this is how is your building, right? Like you have a core here, a bunch of columns. But by the way, calculating the shear lag ratio is a bonus. Like you don't have to do it, okay? I mean, if you wanna do it, you are gonna get an extra 5% bonus, but if you don't wanna do it, that's not gonna hurt your grade. I told you, like, to get the perfect stress on your columns or the perfect normal force on your column. So let's say that your building is something like this, and it's gonna get, from the earthquake, once it shaped, this is the VB, okay? The base shear at the base. So the base shear at the base get transferred to the building, and when we distribute the loads, it's gonna be something like this. And ETAPS, it has a tool that you can get the overturning moment at the base from all the columns. So you have the total moment at the base. And that's actually what created this. Like when your building, which is something like this, get this overturning moment, what happened is, this column is gonna have tension, tension, compression, compression, and then you're gonna end up with something like this. Right? That's how the shear lag is, how it's gonna look like. And the shear lag means normal force inside the column. And that's what you get in these conditions with this distribution of columns. And I told you how to reduce the shear lag, limit the spacing to make the spacing closer, increase the depth of the spandrel beam, increase the dimensions of the column. All this is gonna make the shear lag less. However, let's say if this is a perfect condition, like it was a solid shear wall, and it has this bending moment, like let's say, imagine that this building has a solid section, and this solid section, if we look at the top, is gonna be something like this. And if it's a solid, like, I mean, like if all this is concrete inside, like you having a cross section in a beam, and when you look at the cross section of beam, is gonna be something like this. This is gonna be tension, tension, compression, compression, and this is gonna be linear, I mean like constant, and this is constant, and this is constant, right? This in a perfect condition. If a cross section is exposed to bending moment, this is how the stress strain curve look like. So what happens here, that something lag the shear to make it something look like this. So you need to find out, if you put both of them on top of each other, like let's say we are gonna plot this on top of this. So it's gonna be something, let's say something like this. The thing is, your system only absorbing or only inducing normal forces that can, that has this shape. However, you are losing all this. So if you want to find the efficiency of your system, you divide this, like this area, over the total area of the rectangle. Because you are losing the red, but you are gaining the black. Because that's how your system performs. The more that you get this black curve up, the more it's gonna be better. Why? Because you are making all your cross sections performing much better, absorbing much more load. Like this column is the same like this column, like the same like this column. However, this column is working with full efficiency. And the way that you get to the middle, this column doesn't have efficiency enough to absorb more load. So how we can make it absorb more load? Like this column wanna go all the way up, but this one can't go up. So you need to pull him with you to go up. So you either increase the spandrel beam stiffness so it can pull him up with each other, or making the system more like a cross section, more like a solid cross section. All right. So if you want to find the efficiency, you have to draw this red and measure this delta, and at the end you divide delta over this total delta, and that's how you get. But the thing is, how you can get these green lines, I discussed this in one of the videos. You have to find the stiffness I of everything at the CG of the building. How? And all these columns are not at the CG. So you need to find the inertia of this column, the inertia of this column, the inertia of this column. And all this line is very easy. They all have the same inertia. So if I have 60 columns, I multiply 60, AB cubed over 12. And this is gonna give me the inertia here. If I wanna transfer it here, you multiply the area by the distance from here to here squared. Okay, so I transfer this inertia to be at the CG. Same thing with here, same thing with here. Actually, there's softwares that can do this for you. You can, I don't know, but you can do it yourself by Excel sheet. Same thing with these columns, like this and this at the same distance, and you can transfer them here. At the end, you should find the total inertia for the entire structure. Okay, the total inertia for the entire structure. So you found I. So what I want from this, I want to at the end be able to solve this equation. Sigma equal m over I multiplied by y. All right, so I told you how to calculate it. You need to calculate column by column and sum all of them to get the total stiffness of the entire structure. The moment from the E-taps, you can get the overturning moment at the base. Okay, that's also, there's an E-taps when you click table, there's something called base reaction. And the base reaction, it gives you the shear, the base moment and everything. Why? That's something that you need to find out. Like here's the CG and this is Y. So you will be able to find the amount of stress at distance Y equals 30 meters, or at distance Y equal 20 meters. So you can find it at any Y. All the columns that are at the same Y, they all are gonna be constant, right? So that makes sense. And the more that you approach to the CG, it's gonna be 0 because Y is gonna be 0. So right now you can find the level of stress, but I'm not interested in the level of stress, I'm interested in the normal force. And that's very easy, because if you find the force P is gonna be sigma multiplied by A. You have the cross section of the column, you have the sigma, so basically you can write B is equal to M over I multiplied by Y, and all this is multiplied by the cross section area. And then you will find the normal force in each cross section. Okay, so you will find that your normal force, like if this building doesn't have a shear lag, and by the way, shear lag happens in any hollow section. Like even if the building is something like, if I have a section, this is a solid cross section. If it's a solid cross section, there's no shear lag, it's gonna be something like this. But if it's a hollow cross section, something like this, it's gonna be shear lag. Okay, so that happens in bridges. Like bridges, sometimes there's sections. The section of the bridge is something like this, like, and you have, that's a hollow cross section, and they study shear lag very deeply, more than these buildings, because that's a very important in bridges. Okay. All right, does anybody have any questions so far? If you find this difficult or too much work, you're not gonna lose any grades to do it. I'm just like giving you some extra points if you wanna put more efforts, okay? All right, so let's focus on today's topic. Did you guys practice any of what we have done on virtual work, method of consistent redundant? I know it's difficult, and by the way, it's one of the most difficult topics in structure analysis. I'm not saying it's easy. It has a lot of math, a lot of integration, structure analysis, mechanics, has everything, but I can't promise it's gonna get any much easier, because it's gonna be more difficult. So all this lecture and the next lecture, but this is how structure analysis is. From my perspective, I believe structure analysis is the most difficult classes in civil engineering, especially when it gets to that level. So it needs you to put more effort. When you get to structural dynamics, it's much more difficult. Like what we are doing is nothing when you come to studying structural dynamics and solving partial differential equations and all these things. It's gonna get more difficult. But when you understand these things, here it's gonna go in a different level, okay? All right, so, but if you think about what we have done, we did systematic things. We have an indeterminate structure. Do you guys remember? Indeterminate structure, we wanna find the reactions. So we take this indeterminate structure, convert it to a determinate stable structure, while knowing what redundance that we need to find out, what reaction that we need to find out. Then we draw the bending moment of this stable structure, and then removed all the load from on this structure and put unit load at the remove the redundant. Then we draw bending moments for each one of them, and we substitute in one equation. That's how it is. If you think about this systematic, it's gonna be very easy. The thing is, sometimes I can give you problems that is gonna look scary to solve, but if you think systematic and understand how the concept is, it's gonna be very easy. So the first look on your problem is gonna solve the entire problem. So let's, I'm gonna solve maybe 2 problems just to close this topic. Okay. By the way, I have lots of examples in the lecture notes. I'm not gonna solve them all because it's gonna take forever. We have a lot of content to cover. So I'm gonna solve some. You try to solve the rest of them at home, so that as a practice, so that you can solve the home, okay? All right, so I'm gonna put this. All right, new example. I have see that line. Alright, so I have All right, look at this problem. This problem has different stiffnesses. Like I have this part of the beam has double inertia, 2EI, and this one has EI. Okay, that's the first level of difficulty. You guys tell me, how can I tackle this? Like sometimes if I give you a problem like this, oh, it's a very difficult problem, I'm not gonna solve it. But how this is gonna make a difference for solving? Okay, so you will tell me first, but this is a determinant structure. Like I shouldn't have any problem solving it using the static equation, some Fx, some Fy, some of the moment. But I'm gonna increase the difficulty and put a spring here. All right, so that's, right now it's indeterminate. Why? Because this is like a fixation. Like when you have fixed, that means it is the same like you have hinged, but this is unstable. But once I put a spring here, that's the same like this one. This one has a reaction Y, reaction X, and reaction moment. Same like here. But the thing here is that the K here is equal to infinity. If I told you that this K equal to infinity in a problem, it's like you didn't see this spring. Remove the spring and put fixation. Okay, so that's one of an easy trick. But right now in this problem, K is not infinity. K I'm giving to you, it's a 210 ton meter per radian, and I give you EI 10 to the power 4 ton meter. And I'm asking you to draw the bending moment and calculate the amount of rotation at this point, point A. B, C. So draw bending moment diagram and calculate theta at A. Let's see how we do it. So right now, I know for sure that this is an indeterminate structure. Why? Because if this is a simple beam, I will be able to solve it. And by the way, I forgot to put the load. So the load here is 2 tons per meter, just at this piece. Here, there is no load. All right, so let's see how we can solve it. Same systematic thing. pick a system that is determinant and stable. And I always recommend to remove the spring out of the equation. If removing the spring is not gonna make your structure unstable, remove it. Because it's gonna be very difficult if you have the spring. You are gonna deal with F and delta and all of these stuff. So for me, what I would do, I would make this structure as a simple beam the best thing that I can solve. I love simple beams, okay? I have a simple beam and I'm gonna remove the spring and I'm gonna put this load here. And this one is 2EI and this one is an EI. That's my main system. We call it main system. That's the very thing that I would do. And the second thing is, I look what redundant that I removed. What things that I removed from the system? The moment and this spring, right? So I'm looking for the moment here, right? That's what I'm looking for. So this system is like this system, but I remove the spring and I put the moment inside the spring. And what I'm looking for is the moment, okay? All right, so the second thing that I would do, I will draw the bending moment diagram for this main system, and this is gonna be MO, M original, okay? And by the way, this is not the final moment. That's a moment for the original system. And I'm gonna have another one. It's called M1, and we're gonna know what is M1 now. All right, so this system, MO, has the original load, 2 tons per meter, and I wanna find the bending moment for this system. All right, to find the bending moment for this system, you need to find reactions. I need to find what is the reaction here, and what is the reaction here. So the distances here is 2 and 3. Once you find the reaction, you take the moment here, you're gonna find the reaction here. You take the moment here, you're gonna find the reaction here. Or you take some F1. So once you solve this, you're gonna find that this is 0.8 ton, and this is 3.2 ton. Why? Because this is gonna be 2 by 2 by 1. You're gonna make moment 4, and the reaction here is gonna be 4 over the distance 5, and this is gonna give you 0.8. And the sum Fy is 3.2 plus 0.8 is gonna give you 4. You guys got that? Just do static equations, like solving any simple beam. All right, so the second thing, I wanna draw the MO, the moment. So if you wanna find the moment here is 0, so the next thing, I wanna find the moment here. So the moment here is positive, you can put it down or up, but just make sure that you have the sign right. So for example, I'm gonna put it up, 0.8 multiplied by 3 is gonna be 2.4. So this is 2.4, and that's positive. And I know that the moment here is 0, but the moment here is not linear because I have 2 tons per meter. So that's a 2 WL squared over 8. So W is 2.
Should be that
2 squared over 8. What?
Should be that negative.
This one is negative?
Yeah, the moment.
No, like here's the sign. Like the positive sign, the moment is like this. If the moment this is making like this, that's positive. So you can draw it down or up, whatever you want. So, and here I'm gonna put a parabolic curve like this, and this distance is 1 because 2 by 2 squared over 8 is gonna give you 1. If you wanna draw it, and the other side is gonna be something like this, and that's still positive. And that makes sense. Why? Because there's no distributed load, so that's linear. Once the distributed load shows up, it's gonna be curved. Okay. All right. So I have the first bending moment. Here, M1, it's like I removed all the original loads and I put unit load in the direction of the moment. So here's the direction of the moment. I'm gonna put 1 ton meter, and that's actually is a negative moment. Why? Look at this direction. This is positive, this is gonna be negative. If you wanna assume in the other direction, that's fine. Like if you wanna put the moment this way, that's still fine, but you can do whatever you want. So let's see how did I do it here so that we match the numbers. I put the moment in this direction, 1 ton meter. So if this is negative, I'm gonna draw the negative down there, and I'm gonna have here, this is negative because the moment here is 0 and this is 1. All right, I have MO, I have M1, and I'm done with the first 3 steps. The next step, do you guys remember once we draw MO and M1? If we want to find the theta here, we need to have this equation. Theta 10 plus M, theta 11 equal to delta theta. Do you guys remember? We have similar equation, but it was like delta 10 plus F, delta 11 equal to delta. That's what we had last time. But before last time, we used to have delta because we used to deal with forces. Right now, we are dealing with moment. Once we deal with moment, this equation is transformed to theta and M. So it's either theta and M or F and delta. Depends on what forces are we dealing with. And last time, we used to have delta equal to 0, right? Why? Because we used to have something like this, and this is hinge. But I told you, if this is not hinge, and there is a spring, delta is not equal to 0. This point is gonna go down, right? And delta is gonna be equal to negative K, negative F over K. Same thing with this one. Delta theta is gonna be equal to negative M over the stiffness of the spring. Why? Because M equal K multiplied by delta theta, right? But let's say this is not spring. If this is fixed, what I'm gonna do here? It's gonna be 0, right? Because there is no theta, right? So here's the thing. Here, this thing is fixed, so theta is equal to 0. But right now, I don't have like, if this problem, I give you this problem like this and this, and I put the load here. Right now, delta theta is gonna be equal to 0 because no spring here that allow theta at this location, right? But since I have a spring, so I have delta theta here. All right, so I wanna find delta 10 and theta 10 and theta 11. So you guys tell me, what should I do? How to find theta 10? Do you guys remember from last time? It is the integration of M1, MO, DL over EI, right? That's what we did last time. Delta 10 was the integration of M1, MO, delta EI. And same thing, theta 11 is gonna be the integration of M1, DL over EI. Does anybody have any problem till now? Okay, so I have these. I need to calculate them. It's gonna be a lot of calculations. Maybe I'm not gonna do it with the final answer, but I'm gonna give you a hint what we should do. We're gonna have this, but this has lots of tricky things. You guys tell me, what is the tricky thing in this problem to substitute in this sheet? We need to integrate Q system with O system, or one system with O system. You guys tell me, what are the tricky things that I have?
All the difference of inertias and
Exactly, this is 1/2 EI. So when you integrate this triangle with this triangle, I have this is gonna be, do you guys know what is the value here? This is 3 and this is 2. This is gonna be 0.6. It's gonna be 3/5. Okay? Here it's gonna be 1/5, 2/5, 3/5, 4/5, 1. It's 100%. I mean, like as a 1 from here. Okay? Because it's linear. So I know that the moment here is 0.6. I need to integrate this triangle with this triangle. I make sure when I integrate them here, I have this as 1/2 EI. But once I get here, in this part, it's gonna be returned back as 1/EI. Why? Because this is 2 EI and EI. So the integration is not constant over the length of the beam. Why? Because there's a change of material. So I have to divide the integration into two pieces. One that has 1/2 EI and 1/EI. And actually, you can take 1 EI as a common factor and just put 1/2 when it comes to this part. You can do whatever you want. What is the next trick?
the two different. I don't think we have a figure for that, so you have to do two
Exactly, you have to do submission, like superposition. This is a triangle and parabola. So first you integrate the triangle, like to divide it into two pieces. This piece, you integrate this triangle with this trapezoid. You have a shape for that in the table. Then you integrate this parabolic curve with this trapezoid, so you have three parts of this integration. This part, and make sure that you have 1/2 EI, and this part need to be divided into two pieces. What are these pieces? Here, this one is gonna be a triangle, this triangle, and it's gonna be this parabola. This triangle has 2.4, and this parabola is 1. WL squared over 8. 2 multiplied by 2 squared over 8 is gonna give you 1. So you are gonna have three pieces, you integrate them, and then you get this part. So that's for theta 1, How about theta 1, 1? So you need to integrate this triangle with itself, okay? So that's very simple. Two pieces, not one piece. Why? You can say, oh, I have one triangle, and I'm gonna integrate this triangle with itself looking at the table. But the thing is, it's not uniform. So you need to divide it into two pieces. The first piece is triangle, the second piece is a trapezoid. And you look at triangle with triangle, and then trapezoid with a trapezoid, and do it on two parts. I did all of that here, so you'll find out. All right, so once you have done this, you'll find out that this is negative 3.54 over 10 to the power 4. And when you do this, you are gonna find out that this is 1.487 over 10 to the power 4. All right, so I can solve this equation. Right, so I have theta, so I'm gonna put 3.54 over 10 to the power 4 plus the moment that I'm looking for, and I have 1.48 over 10 to the power 4 is gonna be equal to negative. The moment I don't know, but I know the stiffness. I give it to you here, 2 over 210. So I have one equation and one unknown, and then I can find what is the value of the moment. So once you solve this, you will find that the value of the moment is 0.07 ton-meter. Right, that's a very small moment. So let's say I give you that the stiffness here is 10,000 ton-meter per radian. What do you think this moment is gonna happen? It's gonna go up or go down?
Go up.
Go up. Once I increase the stiffness, it's gonna absorb more moment. Okay, if you wanna draw the final bending moment, so right now I got right now I wanna find the bending moment. So to find the final bending moment, this is a rule. It says that M final is equal to MO plus the moment M that you have here multiplied by M1. Okay? So this moment plus this moment multiplied by this value. So for example, this is 0 and this is 0, so the final moment is going to be 0. But I have this is 0 and this is 1, so you multiply 1 by 0.07, so the moment is going to be something like this. You're going to end up with having a negative moment of equal to 1 multiplied by 0.07, so it's gonna be 0.07 like this, and then this moment is 0.6 and this is 2.4, so it's gonna be 2.4 plus 0.6 multiplied by 0.07, so we're gonna have another moment here which is equal to, I didn't calculate it, so it's gonna be something like this, and this is definitely parabolic, it's gonna be something like that. That is the final bending moment. The more stiffness that you have, you will find that this bending moment is gonna go down and then it's gonna make something like this. If you increase the stiffness, this bending moment is gonna be something like this, and the bending moment is gonna go like that. Until it becomes a full cantilever and you get to the final, it's gonna be like bending moment something like this, if this is a full cantilever. And that makes sense. If you have a cantilever, moment is gonna show up here. If the stiffness is 0, all this moment is gonna go back to 0 and it's gonna be equal to this system, this one. All right? Did you guys understand this part? Is it difficult? I believe, yeah, I know it's a lot of steps, but if you understand the whole theory and then apply the step by step, having a main system, like this, and then draw the bending moment, virtual system, draw the bending moment, substitute in this equation, solve the compatibility equation, you draw the bending moment, it's gonna be done. All right, so right now, all the problems that we have solved, only dealing with one unknown, solving one equation. This is one equation and one unknown. What is this unknown? Is the moment m. But what if there's two unknowns? When that happen, if we get two unknowns? Like, let's say this problem is start to be like this. This is one unknown or two unknowns? What are the two?
The pin.
Let's say, no, I mean like, what are the two unknowns? This one is the same like this one, because I removed the rotational spring. You will tell me, but you put hinge here. The other one was roller, so the X reaction is unknown, right? But that's not unknown because there's no X loads, so I know that X is equal to 0, so it's still one unknown, okay? Because I know for sure that X here and X here is 0 because there's no X reactions, okay? So it's still one unknown. But let's say I make this problem like this, and I put W. How many unknowns?
In this case,
Two unknowns, right? What are these two unknowns? The moment on the left and the moment on the right. However, you can solve this in a different way. How? Cantilever. You put a cantilever, and here the unknown is going to be this reaction and this reaction. Or you can make it like this, hinge, and then the unknown is the moment here and the moment here. Okay, so both of them are right. But let's deal with this using this approach. And maybe you can practice at home and do it with this approach. Okay, same thing like what we have done before. I'm gonna pick a main system. This main system is gonna be like this. All right, and I'm gonna put the original load, W, and I'm gonna draw the bending moment diagram. Draw up or down, just make sure it's a positive bending moment, and here's WL squared over 8, right? Do you guys know what is the final bending moments here?
W square over
12, right? So if we got this number, that means that we are right, okay? Okay, so let's find out how we can find these numbers. First, I got MO. The second step is that I remove all the loads. And I'm gonna put unit load at each redundant, one by one. So first, this is M1, and this is M2. First, I'm gonna tackle M1. M1, I'm gonna put a unit load, M1 equal to 1. Second, I'm gonna make another beam. I'm gonna make a unit load, M2 equal to 1. So when you do this, this moment is negative, because I showed you what is the positive. So this is gonna be negative 1, and this one is gonna be negative 1. All right, I did MO, I did M1, I did M2. Is that okay so far? All right, since I have two unknowns, I showed you last time how I built the equation. If you guys remember, it was something like this. Delta 1O, delta 2O, and then you have a matrix that has delta 1, 1, delta 1, 2, delta 2, 1, delta 2, 2. All this is gonna be multiplied by M1, M2. Oh, this is plus, and this is gonna be equal to, if there's a spring, it's gonna be different, but there is no spring, so I know for sure that thetas here are equal to 0. By the way, this is supposed to be thetas, right? Not delta. Why? Because I'm dealing with moments, but I'm gonna keep them delta, whatever, okay? It's just an unknown, all right? But it should be theta 1O, theta 1, 1. So let's find these thetas, how we can find them. All right, This problem is very unique. Why? Look at this. If you integrated MO with M1, is it gonna be different if you integrated MO with M2? Even that the triangle is on the other side? It's not gonna be any difference. Why? Because this is one and this is one. So, and they are in the middle the same. So they are gonna be the same. So delta, you can try it yourself. Try to find delta 1O and delta 2O. Do you guys want me to remove it and put theta? Or is it okay with you that I put it that way? I think I put it here delta as well. Let's see. Yeah, I put it them delta. It should be thetas because we're dealing with moment. Okay, you guys understand that, right?
Mm-hmm.
Okay, so delta 1O, integration M1 MO DL over EI. It's gonna be the same delta M2 MO DL EI, and then you'll find what is the value of this. So if you look in the tables, you're gonna find that this is gonna be 1 over EI, and this is gonna be 1 over 3, that's the factor, and then this value multiplied by this value multiplied by L. So it's gonna be W L squared over 8 multiplied by 1 multiplied by L. So this is gonna be W L cubed. And by the way, I forgot something. You guys tell me. And this is something that you guys always do, and me too. So the signs, positive and negative. Don't forget to have negative here. Okay? All right, so I got delta 1O and delta 2O. And also there's something also very interesting. Delta 1,1 is equal to delta 2,2. If you integrated this triangle with itself, it's gonna be the same like this triangle with itself. It's the same triangle, just like in a different thing. So you'll find out once you do it, the integration of M1 DL over EI. This is gonna be L over 3 EI. And also we know delta 1,2 is the same like delta 2,1. They are always the same. If you integrated this triangle with this triangle, it's gonna give you the same this triangle. So delta 1,2 is equal to delta 2,1, and this is gonna give you L over 6 EI. All right, I got everything that I need to solve this two equations and two unknowns. So if you put these in a matrix form, and if I put, did I put the negative? Where did I put the negative? I think I put it right. Oh, I put it here. I should put it there. Okay. And these are positive because you integrated negative with negative is gonna give you positive, and you guys understand that. So I'm gonna put negative WL cubed over 24 EI. Because I have EI here, and negative WL cubed over 24 EI plus the matrix of delta 1,1, I have L over 3 EI, and this one is also L over 3 EI. And I have on the diagonal L over 6 EI and L over 6 EI. And all of these is multiplied by M1 and M2. And all of these are equal to 0. That's two equations, two unknown. And I know it's not numbers, you can put them in your calculator, but you can solve this using the principles of matrix analysis. You get the inverse of this, and there's a way to solve it. Once you solve them, you will find that M1 and M2 are equal to WL squared over 12 and WL squared over 12. And by the way, the final answer, when we put this as a final answer, that's what I'm looking for when I give you this in the exam. We always want them in the form of a vector. It's called fixed end forces. Okay? What is the fixed end forces? For this problem, that's special because it's a fixed. So we write a vector that is called fixed end forces. You can put it in the form of a column or a row. And we make like this. Right now, you find that this is WL squared over 12, and this is WL squared over 12. I need also to find the reactions here. You easily can find what is the vertical reactions here, can you?
Yeah, W square over 2, WL over 2.
WL over 2 and WL over 2, because this W is equally distributed in these two reactions. So you have WL over 2 and WL over 2. How about the X reactions here?
0.
Is there any X reactions?
No.
0, right? Okay, so when we write the fixed end forces, we write them this way. This is point 1 and this is point 2, and this is the order, and also the direction. Number 1, you put X reaction. Number 2 is the Y reaction. Number 3 is the moment in this direction. Number 4, because that's what the computer do. Number 5, number 6. So I need a vector that has 6 elements. Each elements match these numbers and these directions. You guys tell me, what should I put in the first one? Let's match this with this.
0.
0. What is the second element?
W over 2.
WL over 2. Because this 2 is matching this one. What is the element number 3?
WL square over 12.
WL squared over 12. What is number 4?
0.
0. Number 5?
WL over 2.
WL over 2. And the last one?
Minus W square over
Negative. Why? Because this in this direction and this in the other direction. So we put negative WL squared over 12. And we call this vector is the fixed end forces vector. Okay? You can put it in a column and you can put it, you understand why we do this when we start the matrix analysis. Okay? So that's the fixed end forces. So in the exam, if I give you this problem and I told you, write the fixed end forces vector, at the end you have to write it that way with that organization and that directions. Okay? All right. So we saw some applications for the method of consistent redundant. We find the fixed end forces, we find reactions. Also, one application that the method of consistent redundant or the flexibility method is to find the stiffness of elements. Like, how can I find a stiffness of an element? That method also help us with that. So let's see. I solved many problems here, maybe you look at them. But, okay, let me start with this. If I have a bar member, like this. Bar means that only takes axial forces. And I ask you to find what is the axial stiffness of this bar. Like, what is K of this bar? Like this bar, we can represent it with a string, and I need you to find what is the stiffness K. That's actually a very simple problem because we know it's a linear element and it is under Hooke's law, so B equal K multiplied by delta, right? So we know that for sure. So, and also we can apply this thing that the Young's modulus is equal to the sigma over the epsilon of the member. Right? So basically, if we were able to formulate this rule to be in that format and we find the value of K, we solved the problem. How? So E is equal to sigma. Sigma is B over A. And epsilon is delta over the length of the problem, right? The strain over the, the deformation over the overall length. So this is gonna be BL over A multiplied by delta. So at the end, if I organize this equation to be like this equation, I can have B alone, and then I multiply E and A over L, and having delta here, this is like this. So definitely this is the stiffness of the member, EA over L, and that's actually something that you need to remember that the stiffness of a bar is EA over L. It's proportional in the Young's modulus, the cross-section area, and the length of the bar. And that makes sense actually. If the Young's modulus of a material is much bigger, that means it's much more strength, okay? And if the cross-section is bigger, that means also it's gonna be more stiff. But if the length is taller, no, it's not gonna be stiff, it's gonna be buckle, it can be broke, okay? So that's 4 bars, but that's very easy and we didn't use the virtual work. So when do you think that we can use the virtual work if it gets more complicated? Like let's say, like the problem that I have here. If I say that I have a bar like that, here and here, but this bar doesn't have a constant cross section. Part of the cross section is 2A and another one is A. And also here, this one EI and 2EI, why? Because that's a beam, has a bending moment. So when there's a bending moment, it's inertia up, inertia out. But if it's a bar that takes axial force, we only care about the cross section area. The inertia doesn't matter when it comes to axial compression and axial tension. Okay? How can I solve this and find the stiffness of this spring? So, as we know that the stiffness, like let's say, that's how actually we can drive a stiffness. If I want to find the stiffness K of any element, like let's say I have a column, and I want to find the K of this column, okay? That's what we do in the lab. Like we take this column in a lab and we put it under compression. We make a compression test. And we put load here B and compress this bar or this column at delta equal to 1 centimeter or something. Delta equal to 1. The final force that we get is the stiffness of the element. Why? Because if you put delta here is equal to 1, B is gonna be equal to K, right? So that's actually how we find the stiffness in the lab. We take the column, we take the sample, compress the sample with 1 unit load, and then if I put 1 unit load, here, B equal to 1, not unit load, unit displacement, and once I put the unit displacement, so the K is gonna be multiplied by 1, and the force that drives this unit displacement is the stiffness of the member. So if I wanna find that, the stiffness of this member, put a unit displacement here. And then the final force that you are gonna get is the stiffness of the member. So let's say that we are gonna put a U equal to 1 here at this location. By the way, this doesn't have any external loads. There's no external load, there's no B, there's nothing. Just a member, I wanna find the stiffness. Because loads can be in many format. It can be in a direct load, or it can be displacements. Like if you have a building and you built your own building and somehow the foundation got a scour, like the sand or the soil run from under the column or under the foundation. So the column is gonna settle down. This settlement is load on your structure, okay? So we are gonna put a unit load here. So once you put a unit load here, you need a force to drive this unit displacement. So some force is gonna be induced here, and some force is gonna be induced here. Once I found these two forces, this is the axial stiffness of this member. And let's find how we can use the concept of virtual work to do this. First thing is, I need to have this system, I need to choose a main system that is determinate and stable. Okay, I'm gonna find out, I'm gonna make it like this. Here, here, and I know that this is double this, the cross section. Here, let's put this as L and L over 2. All right. And I have this as something like this. This doesn't have any loads, all right? So that's the main system. Then I'm gonna put the virtual system like this. And this virtual system, I'm gonna put a unit load. Unit load, the unit load is something like this. 1 ton or whatever load that you're gonna, 1 kips, whatever. So that's, right now we don't have M, we have N. That's NO, which is 0, and that's N1. And N1, you are gonna have a reaction here is equal to 1, and this is under compression. So this is gonna be negative 1. All right? Does anybody have any problem till now? That's the system. doesn't have any load, so N always look like this, and that's the system with a load like this. All right, so the next step is to substitute in the equation. What is this equation? Is that delta 1O plus F. I want to find the F here. That's what I removed, okay? Plus F, delta 1,1 is equal to delta here, right? Okay, so delta 1O is 1O, that's actually very easy. I have NO is equal to 0, I integrated with N1, is gonna be 0. So then I'm gonna end up with F multiplied by delta 1,1. I can find delta 1,1. I have N1, I integrated with itself. It's gonna be rectangle with rectangle. So that's very, very easy. You multiply 1 by 1 multiplied by L. So delta 1,1. This is gonna be 1 over EI. And you're gonna have 1 multiplied by 1 multiplied by 1. The factor is 1, and this is negative 1, multiplied by negative 1 is going to be positive, multiplied by L. So this is going to be L. Oh, we have something. We can't do this. So you have, this is double the inertia, and this is double the inertia. If that was EI, and that's EI, not EI, that's EA. Let's, okay. So from 0 to L over 2, that's going to be AA, and plus from L over 2 to L, that's going to be N1 DL over 2 EA. So what you're going to have now, you are going to do this part first, which is 1 over EA, and that's going to be 1 multiplied by 1 multiplied by 1 multiplied by L, which is L over 2, plus 1 over 2 EA. Same thing, 1 multiplied by 1 multiplied by 1 multiplied by L over 2. So we're going to have, it's going to be, this is 1/4 and then 1/2, so this is going to be 3 L over 4 EA. Is that right? Okay, so I have delta 1,1. I solved it for this one. How about delta? What do you think about the value of this one? This is equal to 1, right? Because that's the delta here. We already put a unit displacement at first. So at the final, I want to find the value of forces that can drive delta here is equal to 1. So you are going to have F multiplied by 3L over 4EA should be equal to delta at this point is equal to 1. If there is no delta at this point, and U is equal to 0, so you're gonna put 0 here, that means the force is 0 because it's a member that doesn't have any load. But since we put a unit displacement at this point, we're gonna put a unit displacement here. Okay, so the final force is gonna be 4 EA over 3 L. And that actually makes sense. Look, when you have this is a constant inertia A, you have EA over L. You increase the part of the inertia, like you increase just half of it. So you end up having more than 1, 4 EA over 3L. If you end up with having the entire cross section that has 2A, you are gonna have here 2 EA over L, okay? All right, so that's also one applications that we apply this method, okay? Does anybody have any questions so far? So from what I see, it's just like it's a systematic problem solving. All what you need to be careful at is the sign, negative or positive. Try, because that's sometimes, I'm not gonna make you lose the entire problem. Maybe you lose 1 point or 2, but make sure that you have your signs right, and make sure that you, if you have multiple inertia or multiple areas, that you divide your integration.
How did it become delta 1 and 0?
This delta?
No, the one that.
This one delta
Yeah.
1O? Because the main system that I have doesn't have any loads, okay? So since it doesn't have any external load, so there's no loads here. That's the main system, okay? So you either have 2 types of load. I can give you a problem that doesn't have any external load but has displacement, so the loads are gonna show up here.
I see.
So if I have external displacement, displacements are gonna show here. But if you don't have displacement, this is gonna be 0. And if you have external loads are gonna show up here, okay? All right, so same thing with this beam. Like, let's say I told you that I I have something like this, and I told you there is no external load. Like, this is the same problem like the one that we solved here. There is no loads. This load is not here, but I told you there is a displacement 2 centimeters here. Somehow you can plug this into the equations and solve the equations. And sometimes I give you temperature, but I'm not gonna do that. I'm just like, that's one way, that's also other problem. Temperature is gonna also another load, because it's making extension. Yeah, but when you have temperature, you are gonna end up having these as unknowns. That's when it's gonna show up, okay? All right, so we're not talking temperature now, we know how this is working now, right? Okay, so this is gonna take us to an interesting topic. All right, so right now we are done with the flexibility method. What is the flexibility method? All what we have done. Unit loads, MO, M1, find the redundance, all this is a flexibility method. Right now we need to talk about solving structure using matrix analysis. I hope that your matrix background is good, okay? So, solving structures using matrix analysis. That is actually, we did some matrix analysis. Like, to solve this, that has some matrix analysis. But we are gonna do it differently. Rather than having deltas here, we are gonna have stiffnesses, okay? So, and that's actually what the computer is doing. The computer is not working that way. Computer work with matrices, because that's the most convenient math that computers can do. All right, so there's 2 methods that use matrix analysis. The first method is called method of stiffness and consistent redundant. And sometimes we call it direct method, and sometimes we call it non-computerized method. I mean, like, the computer doesn't use this method. The second method is called stiffness method. And sometimes we call it generalized method. Or computerized method. And that's what is SAP 2000 and ETABS is using, the stiffness method. So, in general, actually, it's built on this rule. Can you see B multiplied by K, B equal K multiplied by delta? But the thing is, right now, this is just one simple bar. And this simple bar can be described by this equation. The B that you have outside, if you have a force B here, so the delta induced by this B is function in the stiffness of the member. So this is B, if you want find delta, so it's gonna be over K, right? But if you have a big structure, like a building, and that's not, you don't want to find the stiffness of one single column, you need to find the stiffness of the entire system. But to find the stiffness of a member, did you guys remember what we need to do? Like, if I want to find the stiffness of this column, I put a unit B, I put load B, and I keep this load until this specimen goes by unit displacement, goes by 1 centimeter, right? So how I can do this for a structure? To do this for a structure this is gonna be much bigger. This is gonna be something like the F total on the structure is gonna be equal to the stiffness matrix of the structure multiplied by U of the structure, and U is the displacement. But this displacement is not only one displacement, because the structure has many displacements. Like, let's say that this is not only one member, it's gonna have multiple members. Like let's say that you have a structure like this. What displacement that this structure can move? This point actually can move this way, can move this way, can move this way. And this one can move this way, and can move this way, and can move this way. So you have 6 displacements. So this needs to be 6 column, I mean like a vector that has 6 components. U1, U2, U3, U4, U5, and U6, right? And you put the vector here, and the stiffness matrix of the structure is not one single number. It's a matrix that is 6 by 6. And the final forces on this structure, because that's the forces that derive this displacement, and you need a force that derive this displacement, a force that derive this displacement, and you put them in a vector that is 6 by 1. So that's how big it's gonna be. That's why I'm teaching you that the stiffness method right now, when we were solving this, that was a stiffness method, but that was a very, very simple stiffness method. Just one number, 1 degree of freedom, 1 load. But when it's a bigger structure, you are gonna have multiple loads in the direction of these degrees of freedom. And right now, rather than having 1K, like one element with 1 stiffness, you have a structure that has a matrix that describes the stiffness of the entire structure. So, I need to explain something very quick. Let's put it here. All right. So right now, as we said, that the stiffness method is gonna be like something similar. B equal K multiplied by delta. But when we go bigger, so we say F total on the structure is gonna be equal to the stiffness matrix of the structure multiplied by the displacements of the structure. However, F total needs to be explained. Why? Like, let's look at this one. If total on this structure was just equal to this B, that's the force that drives the deformation. But let's say, okay, let's say that I have a problem like this and I have hinge like this. And I want to find out, like let's say that is the degrees of freedom. That's the displacement, because this structure only allowed to move that way, right? There's no other degrees of freedom. There's no other displacement. Here, ux, uy, and the rotation is equal to 0. Here is ux and uy equal to 0. So this is the only u that can be here. And that makes sense. If you have a 1 degree of freedom, it's only one equation. Okay? All right. So we need to find what forces here that can drive this displacement. I can actually, this structure, let's say it has this load and this load. And you have a moment here. Okay? I'm gonna ask you, is these loads actions or reactions? Actions, right? So, but if I calculated reaction, is gonna be something, let's put them in a different color. Let's say I have something here and I have something here and something here. What is this? This is reactions, right? So this F total, we put it that way. We say that F total is equal to the F nodal minus the F fixed end forces. How this is coming from. So F nodal is the direct load at the degrees of freedom. What that mean? Like here I said that I have U rotation. Like I said that I have, this is only degree of freedom that I have. And you have direct moment at this node. That means that we call nodal force. Nodal force is a load at the direction of the rotation, or of the degree of freedom that you have, and it's a load, it's action, not a reaction, so we put it that way. And somehow, these loads that we have here induce rotation here. Like when you put these loads, the thing is, if this is fixed, the loads here contribute with a moment, right? But because we don't have this moment, because this is hinge, this thing starts to rotate. So there's two ways that this hinge is rotating. One of them is because of the external loads that you have here, and one of them because of the load, the direct load that you have on this hinge. Okay? But the thing is, once you calculate the reactions from the fixed end forces, like here, it gets here in this part, FF. So that's why we have it negative. Why? Because it's a reaction, not an action. Okay? So the total force on a node is the nodal force, the direct load on the node, minus the fixed end force on this node. That means the reaction on this node, and it should be negative. So we can write this as that the F at the node is equal to fixed end force plus S multiplied by U. And that's a very, very important equation for the stiffness method. You should have it here. You shouldn't forget it. Okay? So that's the main equation that we need. So when we solve for matrix analysis, the first thing that we need to find out, what is the fixed end forces? Why? Because what we do actually in a stiffness method, like you have like, let's say fixed and hinge. We fix this hinge and we see how much moment is gonna be induced here. And then because the thing is, the real problem is not fixed, it's hinged. But how this joint got rotated, because this was, if it was fixed, it has this moment, but since it was fixed, all this moment was transferred into rotation. Okay, so we put that here, fixed end forces. Okay, then you have the stiffness of the member. You need to find the stiffness of each member of your structure, and I'm gonna show you how, once we find the stiffness of each member, how we can sum up all these stiffness and come up with a stiffness matrix for your entire structure. Okay, and finally we need to find the deformation. Okay, so that's actually how the stiffness method work. I'm gonna show you just a quick example how we do this, like and not on a complex structure. We are gonna work on bars first. Like, let's say if I have a bar like this, and actually we represent bars by spring. Bar is a truss member. We can call it a truss member and has a stiffness scale. You guys tell me, what is the degrees of freedom of this bar? 2, right? You only have U here and U here. This is the 2 point. You'll tell me, okay, but how about the degree of freedom? If the bar is moving that way, it's not gonna induce any internal forces. It only induces internal forces if it's tension or compression. It's inside or outside. So it only have U1 and U2, right? So I know that the element stiffness matrix for this spring is 2 by 2. Like if I wanna find K of this spring is gonna be 2 by 2. Why? Because it has 2 degrees of freedom. If an element has 6 degrees of freedom, so it's gonna have a stiffness matrix 6 by 6. How we can find the element in this stiffness matrix? We can write them like this. It's K11, K12, K21, K22. All right, it's a column by column, let's find them. How we can find the first column of the stiffness matrix of a member? That's actually corresponding to U1, and that is corresponding to U2. Basically, we take this spring, okay? And then we fix all the degrees of freedom. Like we fix this degree of freedom and we fix this degree of freedom. Okay? We fix them, like it's not gonna move. And then first, we put a unit load, let's say it's a spring here. And we put a unit displacement, U1 equal to 1 here, and this one is 0. U2 is equal to 0. And then on the other side, we put U2 equal to 1 and put here U1 equal to 0. And then find the reactions. So if you put U1 equal to 1, you need a force here F to drive this, and F is gonna be equal K multiplied by delta. K is equal to K, and delta is equal to 1, so F is gonna be equal to K. And in the other side, you are gonna have a reaction, K in the opposite direction, right? And both of them are compression. Why? You have the spring fixed here, and you are pushing it that way, it's compression. And the other side, you are gonna have K this way, and K this way, and that's tension, right? Okay, so what is inside the stiffness matrix? The stiffness is the force per unit deformation. We put the unit deformation, so all the forces are stiffnesses, okay? So that's how we manipulate the whole thing. We put a unit deformation, and we find reactions, and these reactions are stiffnesses, because if we multiply the reaction by a unit deformation, is the same thing. All right, so we call this K11. K11 is gonna be equal to K, and we call this is K21, and it's equal to K. What that mean? K11 is the force at point 1 due to unit deformation at 1. And K21 is the force at 2 due to unit deformation at 1. Okay? So what is here? Like here, this one is called K12. What does it mean? That means that this is the stiffness or the force at point 1 due unit deformation at 2. This is, you guys tell me, what is that? K22. What does it mean? The force or the stiffness at 2 due to unit deformation at 2. And that's what we put here. So the stiffness of this member is K negative K negative K K. And we're going to talk more about it next time. Just like giving you an introduction, I'm going to repeat it again next time, how we drive the stiffness matrix of member, okay? All right, I know it's kind of a lot of math to digest, but structure analysis, you guys need to work hard on this, like try to catch up with all the material, because we are going to build on this next time, okay? All right.